some trouble adjusting it, but we will live with it together. I would like be aware, of course, that our meeting is going to be recorded, and as it is being recorded, I'll try to post it on the internet so that you can access it yourself. Our meeting is for the NPRE 402 class, which is the nuclear power engineering course. Let me minimize this here if I can. And we are going to interact through two media. One of them is the World Wide Web, the internet. So here you have the URL, https://mragheb.com, will send you to the portal that I use for all my other courses, and that will also introduce me to you as the participants. It seems it's giving us a hard time, so let us see how to adjust ourselves. Share, not no share here. We need to share the screen, and it disappeared once I had somebody stop share again. Let us and reshare. So please just allow for some adjustments here. In the case of some kind of pressure on the internet, I'll show you how we can proceed with the course, even if we don't have internet connection, because we have a complete set of notes on the web. Our course is a universal course, if you can say it. You could see here the participation or the audience covers the whole world, the United States, India, Egypt, Pakistan, and even Russia. And according to Alexa, we have people from 45 countries that visit our class. So you are part of an international audience. The courses I teach are listed here. If you connect to the portal mragheb.com, I'll keep it updated. You'll find that here is a course that we are teaching this semester. That would be your URL to connect to it. In the fall, the same course is going to be taught, but in that case, it will be face-to-face. Also, the course on the safety analysis of nuclear reactors is going to be taught face-to-face. The last semesters, to show you my areas of interest, I taught the course on wind power systems and a course on energy storage, in addition to our nuclear power engineering class. That reflects the interest in that in a sustainable new future for energy, we need to develop non-fossil sources, and that includes renewables. Wind power systems is one of those developments that we'll see in our future, in addition to nuclear energy. Because the renewable systems are all intermittent, we need to develop systems of energy storage, like pumped storage or using hydrogen fuel cells and so on. And you can access that course lecture note just here from that portal. If you go down lower, you'll find the connections to a course that I teach on Monte Carlo simulation, that's computer science, fuzzy logic and its applications, nuclear radiological safety, and radiation protection in general. I have a blog here that you can access that is material that is not included in the lecture notes. Like last month, I made a presentation to the Delta Kappa Gamma Society. You can access the presentation there. Some, again, material blogs that are not included in the lecture notes. You can have fun over the summer, maybe accessing some of my publications, the economics of wind power generation, for instance, nuclear naval propulsion. These are book chapters, quite a few of them here, invited by editors based on the lecture notes. We have journal papers that you can look at, Lanchester Law, Shock and Awe Strategies. This is more like operations research and computer science. This would allow you to win in any strategies in peace or war, like in economics, for instance. Fusion, fission, hybrids as an early introduction of the thorium cycle. It tells you about my areas of interest scientifically. There are some articles listed here, quite a few videos, and more of them listed for maybe last summer. They are recorded both on the Illinois media space as well as you could see here on YouTube. Of course, I recommend that we follow our this semester's videos. And then you have conference papers with many of the students that work on term papers, the graduate students, as well as very book reviews, technical reports, quite a large number that I was able to list right here. Having said that, we come back to our business today, which is the nuclear power engineering class, which is NPRE 402. And you'll find that this is the URL connection to it for the summer of 2022. You'll find that I'll try to record, give you recordings of the lecture videos. This was for the last summer. And then after we present the lecture, you will be assigned assignments that will be due 1 week from the day of the assignment. They'll be in two formats, the PDF format or the Word format. Let's try the PDF format on that link here. And it gives you the instructions on how we are going to proceed with the assignments in general. Today's assignment, for instance, will be due 1 week from today. And in that case, we get wonderful TAs. We have two of them present with us today. I'll give them a chance to present themselves. You submit your assignments and get your grades graded on Canvas. So in that case, the instructions on how to work with the assignments is to read the assigned reading lecture notes, chapters, not just attend the lecture. You answer the corresponding written assignment. If you have questions about the assignments, I'll have the information for accessing the TA on a TA list link. You submit the written assignments through email to canvasillinois.edu. Please, we request that you use the Word or the PDF format. And in case of internet rationing or the power system, like today, there is a heat advisory, the power system failing us, then in that case, you read the lecture notes without having to come to the meeting. You work on those corresponding assignments. And if the internet totally fails us, all the points that you would have accumulated in the assignments as well as the exams, we'll have 3 exams, 2 midterms, and 1 final. Bear in mind that we are going to have lectures that can last 2 hours at a time. All right, having said that, we go back to our class here. The assignments, you find that I provide you, the calendar is going to be updated, obviously. We are meeting on Monday, Wednesday, and Friday from 10 till about noon. And you'll find that we have access to a complete set of lecture notes here. They are divided into parts. It's a historical part, the dawn of the nuclear age, the modern nuclear science, the radioactive processes, fission systems, fusion systems, space nuclear power, transport and diffusion reactor theory, radiological science, nuclear safety, and nuclear applications. We'll not be able to cover all those chapters in our short course here, but you will be able, once from what we are going to cover, to read on your own. The rest of them may be sitting on the beach having fun. Without delay, we have also a chat room that is opened, and in that chat room you can ask questions from the TAs. Will try to answer your questions. We have two of them present. Anshal, I think if we show the gallery here, Anshal is shown right here, as well as Mr. Alvaro. I don't know how to get the picture. They have changed the settings from what I have used before. Let's see if I can get, it's a nice thing if you can show your picture. It will give it.
Good morning, Professor.
Okay, Anshal is talking to us here. Alvaro also probably is here. Again, the setting of the internet has changed, so be patient for me to adjust to it. Anshal is shown right here. She's very dedicated to the class, and she has been done a good job forever. There will be a first midterm, a second midterm, third midterm. There will be announced here. The assignments will constitute 40% of the final grade. Each one of the tests would be 20% of the final grade. I follow a linear kind of grading. I do not curve the grade. So meaning that you are really competing against yourself. You have to do your best. You can qualify for the A minus or A plus, all of you. You are not competing against the rest of the class. The calendar will be adjusted. Obviously, this was the last semester's calendar. And in that case, we don't lose our time. You have lots of energy. So let us use your energy in covering the preface or a general introduction to the course. Let me get rid of that part here. We don't need it. And the title of our course is Nuclear, Plasma, and Radiation Science. And definitely it's an invention that of the future, because the existing systems is just the Model T of nuclear energy applications. And the applications that we are talking about started, unfortunately, as we'll see in the first chapter, in the use of nuclear energy in a destructive way in the nuclear bombing of Japan in the Second World War. But afterwards, humanity discovered that it had to use the power of nuclear energy for peaceful applications. And that was a commitment by the United States, the larger power after the Second World War, by one of the best presidents in the history of the United States, Dwight Eisenhower, shown here on the face of the Time magazine. And he gave an address to the United Nations. And this is a quote for what he said right there: "To the making of these fateful decisions, the United States pledges before you, and therefore before the world, its determinations to help solve the fearful atomic dilemma, to devote its entire heart and mind to find a way by which the miraculous inventiveness of man shall not be dedicated to his death, but consecrated to his life." So this was really one of the best presidents in the history of the United States. And that was commemorated in a stamp on Atoms for Peace and the commitment of the United States for the peaceful applications of nuclear energy. And that's what we are involved with in that course. Basically, his words: to find the way by which the inventiveness of man shall be consecrated to his life. Nuclear energy in the history of mankind is the same as the discovery of fire. Both of them are chemical processes, but nuclear energy, as fission and fusion, are nuclear processes. They do not deal with the atom per se, but they deal with the nucleus of the atom. The National Science Foundation released what it called, quote, Science and Engineering Indicators in 2014, unfortunately, including statistics that detail that what Americans know about science. And the unfortunate aspect of it is that just 74% of Americans know that the Earth revolves around the sun. Unbelievable. So you are not part of that 74%, and you are very fortunate about your knowledge about our universe. Cosmologist Sir Martin Rees gives us a picture of why we stand in our cosmos or our universe. Here we are, humans, as our size is in the 1 meter, and if it's in centimeters, that's 100 centimeter. But the cosmological scale can go up to 10 to the 5th centimeter. This is mountains. If you take the size of the Earth, you jump by several orders of magnitude, then you have the solar system, then you have our galaxy, and then you have the whole cosmos. But that scale goes in the opposite direction too. Here we are in the middle of it. You have bacteria, you have the DNA structure, atoms, molecules, and then the composition of the atom itself is neutrons and protons, and the protons and nucleus themselves are even small. Where do we stand in our interest in terms of energy is described by a Russian cosmologist, who came out with what we call the Kardashev cosmological stage. He suggested that the level of civilization in general takes 4 forms: type 0, type 1, type 2, and type 3. And he measured the level of technological civilization in terms of the use of energy. And I'll expand on this a little bit more. The type 1 civilization would be a civilization that uses up all the energy from its star. Then he went on its own planet. So that would be using all our wind resources, fossil fuel, and nuclear resources. The type 2 civilization, he considered it as civilization that can use all the energy available from its star, or in our case, the sun. And then a type 3 civilization would be civilization that uses all the civilization from its galaxy in that case. So he suggested that an advanced civilization may have a rule that protects its security and safety. And the 3 base classes depend on the power level. And let us define power here as energy per unit time. And when you take the system, the SI system of units, that is Système International, the unit of energy is joule. And of course, a unit of time is second. When you take 1 unit of energy, 1 joule per second, we like to call it the watt unit, basically honoring Mr. Watt, who invented the steam engine. In the type 1 civilization that Mr. Kardashev talked about right here, he suggested that the level of use of energy is 10 to the 16th watt. So that's 10 followed by 16 zeros of watts. So they use all the energy in their own planet. Type 2 civilization is 10 to the 20th watts of power. That in that case, they use all the energy in their star system. And type 3 civilization, 10 to the 36, that would be using all the energy within their own galaxy. Some astrophysicists even expanded the classification by Mr. Kardashev into a type 4 and type 5 and even an omega level. And I'll let you read about it for your own fun. But some even other cosmologists came up with other descriptions. They, instead of describing the level of civilization as the use of, depending on its use of energy, they describe it in terms of the use of information. So they count how many bits of information a given civilization uses. According to cosmologists, I'm not talking about it here, but I might add as a note, Mr. Carl Sagan, he passed away. He suggests on some kind of a formula on a scale of 1 to 100 that we are right now at the 0.73 level, or 0.75, just to be close to that 0.73 on the scale of 1 to 100. So we are still in terms of civilization, in terms of the use of energy at a very early stage. Basically, we are still a young civilization technologically. It is interesting to think that in terms of using fossil fuels, we are really using only dead plants, trees that turned into coal, or dead animals, plankton in the ocean that turned into fossil oil, which we call petroleum. Oleum in Latin is oil. Petro means petrified, means fossil oil. It is hoped that we can reach as a human civilization, technological civilization, the type 1 level in 100 to 200 years. So you'll be part of it, your children and your grandchildren, if we do not destroy ourselves by some stupid filters, as they're called, like inventing through gain of function research new viruses that can destroy humanity, or from nuclear war, or basically this is what's called filters. And when we talk about the filters that can destroy our technological civilization, we have to infer what Mr. Enrico Fermi, a great scientist that built the first nuclear reactor, the Chicago Pi #1. We'll cover that in the next chapter. In a meeting or at lunch with some of his colleagues, he came up with some kind of challenging question, and it's named the Enrico Fermi, or the Fermi Paradox in short. He said, if the universe is so big, where are all the aliens? And that's a word, aliens, now being used as in terms of what are other technological civilization. The SETI project, the Search for Extraterrestrial Intelligence project, tried to detect any kind of signals from other technological civilization and failed miserably so far. Another statement of the Fermi paradox is, don't you ever wonder where everybody is? And that is has become called the Fermi paradox. The Earth is 4.64 billion year old, as we know. It is a result of an event where a star collapsed on itself. So we are the ashes of a cataclysm where a star became a supernova, exploded upon itself, spread the remnants of the explosion in the universe, and were caught by our star, the sun. We know that this is a young event because the age of the universe, as we know so far, is 13.7 billion years old. This is the distance or the time that it takes light to reach us from the farthest part of the universe. So Fermi suggested over that 4.6 billion years, there should have been other technological civilizations, but we don't see them. We might be the only one in existence. So there are different theories that try to answer the Fermi paradox, including that the possibility that alien life forms in the oceans can exist below a planet's surface. If you have heat from tectonic phenomena, maybe in Europa, but it has an ocean that is covered with ice, maybe there is life there, and that's some kind of the holy grail of cosmology today. The question is whether there is a great filter that limits the continuous existence of other forms of technological civilization. So if we are optimistic, we can say, oh, okay, we are maybe the only technological civilization in existence. We are here. We are just too early. No other civilization exists yet. And it is our destiny to spread life to the rest of the known universe. And in fact, we have been trying to do that. But the farthest that we reached in the universe is the Apollo missions that reached the surface of the moon. Some of you may join NASA and or even with plans to revisit the moon back again. So I invite you to interview with NASA. We have some of the students taking our class here who have been hired by NASA. So the pessimistic approach, on the other hand, is that there are some filters, or quote, some steps and hurdles to technological civilization are so improbable to pass that virtually no one exists. And there are events that we don't have control on, like an extraterrestrial object, maybe a comet or a hitting the Earth, or an asteroid. And we know that 65 million years ago, that led to the end of the era of the dinosaurs. But that raised the era of the mammals, which we are here today. And we would like to be careful in terms of our technological civilization, not to create our own filters. Gain of function research, for instance, which is suspected to be disguised for biological weapons development in the USA, France, UK, Canada, Russia, China, and even Australia. We are living that problem today. There is a suspicion that that virus was created as part of biological defense, or really offense in general. All right, so this is where we are in our universe today. We may be leading the spread of life in the rest of the universe. Again, if we think about our technological civilization in terms of energy use, we'd like to study how much energy is used in the United States. Particularly, our interest is in nuclear energy. As of 2019, we had 59 commercially operating nuclear power plants. Some sites of nuclear power plants can have 2 or 3 of them. For instance, can have the Indian Point Energy Center in New York had 2 reactors. And you find that a total of 97 reactors have been operating in the United States, in 29 states in general. A typical size of a nuclear power plant is 1,000 megawatt electric. And we mentioned the unit of power in that case. So watt, mega in Latin means a billion. Mega is a million, and giga is a billion. A million is 10 to the 6th power, and a billion is 10 to the 9th power, and then we go to trillion, which would be 10 to the 12th power. This is what is called the Sankey diagram, developed at the Lawrence Livermore National Laboratory, and it describes to us what are our primary sources of energy and how we convert them into secondary sources of energy. So what are the primary sources of energy? Well, solar energy, nuclear energy, hydroelectric, wind, geothermal, natural gas, coal, biomass, and petroleum. Notice that the renewables, say if we take solar and wind, are still a very small proportion of our primary energy use. Most of our energy use still today is primarily petroleum, natural gas, and coal. We are interested in electricity production. You'll find that 8% of our primary energy is nuclear, 8.42%, hydroelectric and wind, and coal are really used to produce electricity. Contrary to some general perception, you could see that petroleum is not used to produce electricity. It's primarily used in the transportation system, like cars and trucks. Other than the uses of the primary and now secondary uses of energy is, of course, industrial uses, commercial uses, and residential uses of energy. You notice that electricity here is feeding the residential, commercial, and industrial purposes, whereas coal is primarily feeding the transportation system. When we transform the primary sources of energy here into useful sources of energy, we entail an efficiency process. We have to reject part of that energy to the environment in the thermodynamical processes that we use. And you find that if you add up that 10.7 plus 8.9 plus 25 plus 28, these are units of quads. So what is the quads? The quad is a unit of energy that is defined in terms of the quad is 1 quadrillion BTU. So this is a unit of energy in the, not in the SI system of units, that's now the British system of units. So BTU stands for British thermal units, and 10 to the 15 is the third level going beyond the trillion, which is 10 to the 12th power. The quadrillion is 10 to the 15 as power. It's the same as 1.05 exajoule or 10 to the 18th joule. Coming back to the Sankey diagram, you could see that I have shown it in several years. That is in 2017. The United States used here as primary energy. If you add those number of quads of energy here, 97.7 quad, then I show it to you in 2018, it didn't change much, 1012 quads. So in that case, when you take the number here and you divide by the 101, you get for residential, commercial, industrial, and transportation, you can estimate an efficiency. The efficiency is the useful energy that we get from the primary energy. I'm asking you to just go through that exercise. Notice that in the end, from that 101 quads of primary energy right here that we feed into the system, we get energy services here. If you add this one plus this, plus this, plus this, we get 32.7 quads of useful energy. The rest is energy rejected to the environment in the conversion process. So it behooves us as engineers to minimize that amount of rejected energy by developing more efficient processes. But if you take 32.7 divide into 100, well, it tells you that the efficiency of our energy system is no more really than 33%. So that's a very low number. We are turning our primary energy and making it useful for applications of transportation, residential, commercial, and industrial with an efficiency of only 33%. That is something that to think about as you start your careers as engineers. In 2019, the same number of units of quads has been used with the same efficiency, 33%. So 1/3 is a good number to remember in our use of energy. The unfortunate thing in our use of energy is that it is not a sustainable source of type of energy system. You notice that here the dependence is, even for the generation of electricity, is the dependence on the fossil fuels here, 32 quads of natural gas, 11 quads of coal, and 39 quads of petroleum. As I suggested, these depend on, well, they all depend, all sorts of energy depend on nuclear energy, because that's energy that comes from the fusion reactions in our star. The sun, it is converted to wind and solar energy on Earth. Solar energy becomes photosynthesis, that becomes coal and petroleum. Over 200 million years, the Earth has created reserves of what we call the fossil fuels. But all of them release carbon dioxide to the atmosphere. So we are poisoning our atmosphere and heating it to the point where it can become unlivable. I repeat this, in some part of the world, in 2050, if the current consumption of natural gas, coal, and petroleum continues, some people suggest that some part of the world, like India, would become simply unlivable. Not only that, and we are polluting our environment by releasing the carbon dioxide that stores the energy in those fossil fuels, but they are depletable. These are 200 million years of storage of energy from the sun, and we are using it within 200 years of our technological civilization right now. So it is inevitable for us that we have, in terms of sustainability, to develop for the future the sources that we call renewables, wind, solar, hydroelectric, and obviously nuclear energy comes to the fore. To show you some ideas about how energy, in fact, is fossil fuels are not part of our future. I show you here the curve that is described as peak oil. And it shows us the billions of barrels of oil that were discovered per year. So this is billion, giga for billion, giga, billion per A. A stands for annum. Annum in Latin is year. So that is per year. And you notice that in the 1960s, 1940s, 1980s, there were discoveries of those oil or petroleum. But the discovery of new sources of petroleum is coming down by 2020. And the discovery that is expected in the future or future discovery is also very low. Whereas you could see here that the consumption rate or the production of those discovered oil supplies has increased and up and down. We are here almost at a peak, but there are no discoveries. So the big worry that we have to worry about in terms of fossil fuels, in addition to the pollution that we get from it, is definitely their depletion. We'll not have them in the future. We'll not have a sustainable system unless we combine renewables with nuclear energy for a future. And you'll find that the production has, in fact, peaked already in several countries. So this is a graph of the conventional oil. When you drill a well and just get the oil out of the strata underground, you don't use secondary methods like fracking or hydraulic fracturing. You find that in Denmark and the Netherlands, Norway, the United Kingdom, all of them have reached already what is called peak oil in 2000. They have depleted the resources of their oil from the North Sea. And so that is happened already. So you find the UK, for instance, switching big time into wind energy and nuclear energy, and Germany switching to solar energy on a big scale. This tells us here really how the conventional sources of oil have peaked. This is the crude oil on the condensate production in million means a billion barrels per day. You could see here that the production in the United States, in the lower 48 states, has reached the peak in 1970. People designate this as peak oil. There was another peak that came up by the discovery of oil in Alaska. So, well, that got us another peak to 1985, and then it kept coming down, and in 2019 we reached another peak, but that does not come from the conventional oil. It comes from what's called the tight oil that is produced from hydraulic fracturing, and you can read a chapter on that topic later on, which also is depletable sooner or later. So the use of nuclear energy is part of our future, and you can read more detail about it. Only nuclear energy will supply us with what we call base load electricity that produces power for most of the day for industrial, residential, and commercial purposes. If we use the renewables, you'll find that they are sources of energy that are not very dense, so they take a large amount of land. So you could see the solar collectors and the wind turbines taking large amounts of land. So we need the level of density in the production for basically the base production of energy, as we'll describe it later. You find here that when we produce energy, there are some detriment in terms of they're causing pollution. And when pollutants find their way into the human system, into the lungs for sulfur dioxide and nitrogen dioxide. They turn into nitric acid and sulfuric acid. So they cause really death. And the largest amount of death that we get per terawatt hour, terawatt is a unit of energy multiplied into hours. So it becomes power multiplied into time that gives you energy. Per unit of energy produced, this shows us here that we have about, let's say, 28 deaths per 1 unit of terawatt hour of energy from coal. There are also deaths from accidents from coal. You hear every once in a while of mining being buried, unfortunately, in the coal seams underground when they're mining it. Petroleum is the second next deadly or risky source of energy after coal, as you could see here. Biomass causes pollution. Natural gas is now the main source of energy that we use in the United States for producing electricity. If you look at nuclear energy, you cannot find really, well, there are maybe 1 or 2 deaths in some of the accidents that happened in Fukushima, for instance. The deaths were 20,000 from the earthquake itself and the tsunami, but 2 people maybe have succumbed to the accident itself at the plant itself. You cannot find deaths on that scale. You cannot even show the deaths from accidents. So nuclear energy presents itself as a safe source of energy. If you compare it to the other sources, people seem to ignore that we get pollution from coal, petroleum, and even from biomass. So there is a trend in energy usage. You could see here that from 2015 to 2017, coal decreased in its use from 15.7% to 14%. So that's a 10% reduction in the use of coal in the United States. In that case, we are retiring our coal power plants for not in addition to the pollution that they cause, also because they have basically aged, they have become too old, and any technology has a lifetime for its usefulness. The 2 growing sources of energy, as you could see here, solar energy growing at a rate of 46% and wind power 30%. So we are on the right track in terms of using renewables. They are replacing our coal production of energy in general. Nuclear energy has not really changed much, even though other parts of the world have recognized the need for nuclear energy. The United States has not yet, or is in some kind of a doldrum. It is undecided. We have only 2 nuclear power plants being built in the United States, whereas the rest of the world, like take, for instance, the United Arab Emirates, they have this producer of petroleum and oil. They have built 4 nuclear power plants looking for a future where nuclear, solar, and wind will be the predominant source of energy. So you find here that petroleum, if it's a supply source of 37% of our energy, you find that it is used primarily in the transportation system. Natural gas also is used in the transportation, industrial, residential. It shows you the different percentages, and I'll ask you to think about it. You notice so far nuclear energy is used 100% in the production of electric power, which is 40% of our energy production. The residential, commercial, 10%, industrial uses 20%, transportation is 30%. Again, notice here that transportation is primarily petroleum. Petroleum is not used to produce electricity, but nuclear energy at that point is primarily to produce electricity. In the future, we discover that there is more need for freshwater supplies than electricity. So in the future, we might consider nuclear energy. We should, in fact, consider nuclear energy for both the production of electricity and the desalination of salt water. And if you get fresh water. I'll jump into that right away here so that I don't forget it. In that case, in arid areas of the world, across from oceans, you can use nuclear energy to produce electricity, use it in industrial processes, build large cities, but also dissolve seawater. Just by evaporating seawater, you get fresh water like the sun does on the oceans in general, creating clouds, and that fresh water can be used in agricultural purposes. So in that case, we can supply the world population with industries as well as food supplies. This is what is called the agro-industrial complex for arid regions of the world. And in fact, you find here from those nice pictures generated by NASA that we are turning our planet into a living, almost like creature. These are the lights in different parts of the world at night. And you could see the higher population centers, Europe, the United States, Japan, India, South America, here are extending our activities over the night by using sources of energy. If you look at, for instance, the Nile Valley, you could see how the intensity of the use of energy is there at night. But all that area here along the Mediterranean is arid land. It's not being habitated, it's not planted, and the world population is increasing, so nuclear energy can help us really plant those areas also along in the Sinai Desert here, around the Red Sea. This would be Jeddah in Saudi Arabia, that would be Jordan here, Amman, this would be Palestine, Israel, and so on. Notice again another picture here from NASA that the population centers are very highly concentrated, and these are all desert areas next to the oceans that nuclear energy can provide with fresh water supplies. That's hopefully in our future. This is the electricity consumption in 2016 from the Energy Information Administration, EIA. You can go to their website and get the latest numbers. Hydrocarbons, coal, and natural gas is 81% of our use of energy. Again, I repeat it here, we are using dead plants and animals for our energy supply. We have available to us nuclear energy, but it provides only 8.7% of our energy supply. That's people get confused here. Let me clarify this. That's 9% of the overall energy supply, but from electricity generation, for electricity generation is 20% nuclear sources. Some countries, as we'll show, like France, generate 70% of their electricity from nuclear power. Why? They don't have the benefit of fossil fuel supplies, coal, oil, or natural gas like we have in the United States. Hydroelectricity is only 3%, wind 2%, solar 0.6%, geothermal 0.2%. And these are the renewables. So really, humanity has to emphasize the use of the renewables in addition to the nuclear energies. For sustainability, again, it's a matter of depletion of our nuclear sources. That's more detail, and it shows us here the sources of electricity in the United States. So if nuclear energy is 9% of our overall energy supply, it is a source of 19% of our electricity. Most of our electricity is produced by coal, 27%, and natural gas is 35%. Both fossil fuels, dead plants and animals that are going to be depleted. I repeat the depletion argument here. It is not just the pollution argument that stands, but the depletion. They're not going to be there in our future. In a sustainable technological society, we really have to develop the renewables, the wind, biomass, solar, geothermal, hydroelectric, in addition to nuclear energy, because these are not going to be available to us in our future, or they will be available to us at a level where the energy you spend for extracting them does not exceeds the energy or is equal to the energy that you get out of them. Think of it this way, about it this way. If you want to produce petroleum or oil, You have to explore for it. You have to drill for it. You have to pump it out. You have to refine it. You have to send it to the population center, say to use in your cars. And once the energy is released out of the petroleum, you want to have energy that is more than what you spend to produce it. Otherwise, it may still be available, but it would be stupid really to spend as much energy as the energy that you get out of it to produce it. So again, the depletion problem should be one of our main considerations in considering nuclear energy, which is the topic of our class here. In addition, we have, of course, a problem of releasing the carbon dioxide into the atmosphere, as well as methane gas. When you heat the atmosphere gas, the permafrost that is storing methane all over the world releases the methane, and the methane as well as the carbon dioxide are greenhouse gases. So this is annual temperature above and below average over the latest years, according, I think that's University of California at Berkeley data. All right, so in that case, we established the need for nuclear energy. Nuclear energy is environmentally kind of sound in that it applies, it takes a very small amount of land to produce it. It's a very highly concentrated source of energy. This shows us a South Texas project. You find it surrounded by 22,000 acres nature preserve. That is not pie in the sky. These are really ducks and geese and flying there. And that is as far back as 1989. That is in Texas. And as I suggested, the third world countries are discovering that for sustainability, they cannot depend on fossil fuels. These are 4 nuclear power plants. They're called the Paraka plants. They're built in the United Arab Emirates. Each one of them is about 1,400 megawatts, and they are a consortium that from South Korea that built those plants. So third world countries are understanding that nuclear energy is part of their future if they want to continue their civilization. In terms of sustainability of energy and electrical source, engineers and scientists are developing today what we call the smart grid. So what is a smart grid in energy? A diagram will show it to us. It is being considered or visualized or thought about in terms of the Internet of Things. And the Internet of Things is designated now as IoT, and the version of it applies to the electric grid concept in general. So in that case, you'll find that we have 5 components of that smart grid. We'll still need centralized baseload power production. That would be nuclear, hydroelectric, coal, and geothermal power stations that do not need, that are not very flexible in meeting the energy demand. So the energy demand varies over the day. In the morning, it's up high, and then afternoon is lower, and then it increases back, and then goes down over different periods of time. In a situation like today and tomorrow, where we are having heat events, the use of electricity for air conditioning increases. In a situation like a year and a half ago in Texas, where it was too cold, you need also power generation, or else people died. In fact, some people died when Texas, because its grid system is not connected to the North American grid of Canada and the United States, are connected to the Mexican grid system. People died in that case. So in that case, we need centralized base load power generation. But the trend in energy production for a sustainable future is also considering the addition or the of renewable source. In that case, it would be wind, solar, thermal, and solar photovoltaic. A problem with the renewable sources is that they're intermittent, meaning that the sun doesn't shine 24 hours, obviously. On a cloudy day, there is no sun available, so you cannot have solar energy. The wind doesn't blow all the time, blows only on land 30% of the time, and on water on the ocean 40% of the time. So if we want to implement renewable energy sources, we need to develop energy storage systems. In that case, the excess supply of wind can be used in pumped storage or hydrogen production or flywheels, many methods for energy storage that I mentioned earlier in the introduction. Batteries, flywheels, hydrogen, and stored reserves. So these are three components that we see as part of the future Internet of Things. And in addition to the centralized power production, there is a way for producing decentralized generation. So if somebody has a piece of land where he can build a wind turbine and place some photovoltaics on people, in fact, in California and Arizona, New Mexico, are in placing now a solar collector photovoltaic on the roofs of their homes. This is going to become a private and industrial consumers products. And you could see around town here, at least one or two businesses have their own private wind turbines in that case. So those four forms, let me show them all together here. The centralized power generation in the energy Internet of Things, the renewable sources, the energy storage, and the decentralized generation have to be turned on and off depending on the need. When there is a need for heating, you have to use your backup systems, maybe natural gas turbines, as you could see it along Highway 57 if you head to Chicago. Around Kankakee, there are quite a few of those gas turbine plants. And the decentralized power generation, you need a control system that turns off the plants on and off. And this is the control system of the Internet of Things. So this is in our future. And for anybody who likes the idea of working in energy, it guarantees you a job and a way of making a living in your future, because engineers of all disciplines are going to be involved in the development. In fact, the interesting thing is that this Internet of Things is already developed, or the countries that blaze the trail is France. It shows us here the energy supply, source allocation, electrical power production over, this would be 24 hours here from midnight to the next midnight at the time of the day of 17, maybe 5 in the afternoon. This is the allocation of energy supplies in France, and you can access their website and find how much energy they're using. You could see the color here. This is 48.894 megawatt, or millions of watts of power. Megawatt means power, not energy. Power, which is nuclear. So they depend basically on 70% of their energy here on nuclear energy. That is France. They supplement it with this. This is the color here of hydroelectric power. And then on top of it here, they have gas. Gas here in French means natural gas in that case. Very little coal and very little oil in France. And an interesting aspect of it is that part here. You notice that part here is solar energy. And solar energy is not available really all day long, as you could see. It starts here at 9 in the morning and then fades out at 3 in the afternoon, 15-hour here. And then they have some parts of their energy that is stored. You could see this part here is 53, that's pumped storage, 53 megawatts. So they pump the water up when they have an excess of energy that is not needed, and then they retrieve it back as hydroelectric power. And the French are smart enough. You could see this part here, here, and here. This is now energy that they exported or they sell it. And notice also that the energy needs in France follows a curve. At midnight, people are sleeping, so the energy needs are low, but then comes 8 and 6 in the morning, people start going to work, So the energy needs increase, and then over the day they decrease. And then in the afternoon, when people go back to work, that should increase back again and then go down for the next day. So this is the idea of the Internet of Things that the French have already using. By law in France, their nuclear power plants are meant to be load following, meaning that if there is a demand of electricity, their plants are designed, nuclear power plants in France are designed to be able to follow the load. Not so in the United States, unfortunately. So in that case, you find that sometimes the nuclear power plants pay the wind producer money so that they don't shut down the plant, because it becomes very hard to restart any thermal plant, not just nuclear, but coal too, to restart it. So the price of electricity can go negative for nuclear power plants in the United States. For those of you who will take part in the design of nuclear power plants in the future in the United States, they have to be designed to be power load following. And I described to you how that can be done here in the text. All right, so this is our energy picture. You'll find that energy is not just a need for society, but it is a right, a human right for society. You find that the United Nations General Assembly of ratified what's called the Universal Declaration of Human Rights. Article 25 states that, quote, everyone has the right to a standard of living adequate for the health and well-being of himself and his family, including food, clothing, housing, and medical care and necessary social services, and the right to security in the event of unemployment, sickness, disability, widowhood, old age, or other lack of livelihood in circumstances beyond his control. So it is not just a goal, but it is a human right for all of humanity. So the development of nuclear energy in that case, as a replacement of the fossil fuels that are being depleted, is a must in our future. And according to the AIA, this is unfortunately how the world supplies of energy are being used. Nuclear energy worldwide was 4.9% in 2011, little hydro, little renewable, and the total dependence, as you could see here, on oil, coal, and NG stands for natural gas. These are depletable sources. They are not in our future for a sustainable technological society. We risk basically extinction if we do not replace those depletable sources with the renewables, hydro and renewables, as well as nuclear energy. And there is a lot to be replaced. So your future and the future of your children depends on it. As I suggested, some countries are more biased towards nuclear energies than others. France, as I suggested in the previous, their Internet of Things diagram, depends on 70% of its energy from nuclear. So this is the 4-unit nuclear power plant station in northern France. They're very proud of what they have there. Their school children are taken to visit the plants. And these big towers here are not the nuclear power plants themselves. That's another 4-unit Canetan 4-unit nuclear power station. The power plants are here in those containment structures here and here. These are cooling towers, basically cooling the coolant for the production of steam. Once nuclear fuel is used and energy is produced from it, as you could see here, it is stored in underwater for a period of time until the radioactivity is decreased, and then it's either returned back to the ground where uranium has been mined in the first place, or recycled to make it into fuel for burning into the nuclear power plants in general. Again, you notice that for electricity production as of 2012, the dependence is primarily in the United States on natural gas and coal. Nuclear is only 19 or 18%. And so that is the figures that we have to live with. The energy consumption in the United States, as you could see here, petroleum, natural gas, coal, and it's all dead animals and plants. nuclear energy total 9%. Renewable that is coming to the fore now is solar, geothermal, wind, biofuels, sometimes wood is used, and hydroelectric power. So our future really is to increase that part of the renewables and the nuclear power generation to replace the depleting coal, natural gas, and petroleum, and they are depleting. The cost of electricity is reflected in that case. You'll find that the renewables in terms of the electricity costs, that's what you pay on your bill when you pay for electricity every month, in cents per kilowatt hour. Kilo is the Greek prefix for 1,000. So that's 1,000 watts. We define the unit of the watt as 1 joule per second. When you multiply it into hour, 1 hour is 60 minutes, multiplied into 60 seconds, then that becomes, you are paying for a unit of energy, not a unit of power. So for hydroelectric power, that's the cheapest, 4.6 cents per kilowatt hour, coal 6.6. Nuclear is very competitive to geothermal and coal. Still, wind is very expensive and solar is more expensive, but technology and the economies of scale are bringing those numbers down. So they are going to be part of our future. This is the total system levelized cost of electricity. When you say levelized, meaning that you compute it over a 20-year period, not just present value, because you have to take into account the effect of the interest rate and the inflation rate. You'll find that still solar is the most expensive source. This is solar thermal, where you use a thermodynamic system by heating the water and using steam to produce electricity. Photovoltaics is cheaper, but you could see here that wind is a good choice in terms of 50, let me see, the units here are, I think, cents per kilowatt hour. Hydroelectric and nuclear energy, advanced nuclear is very competitive with wind power generation. And these are the two sources that are considered for the future. What's the advantage of using nuclear energy in the United States is what we call the capacity factor. It's a time over which the plant is available to produce power for you. It is that, and you find that the capacity factor of nuclear power plants is 91%, meaning that you shut it down for refueling or maintenance only 9% of your time. And that affects the cost of electricity. Coal is 72%, natural gas 41%. The unfortunate aspect of wind is that its capacity factor or intermittence factor is 20% onshore, 40% offshore. So in our future, we'll find more wind parks built on the lakes and the ocean surface. Thermal, solar, and photovoltaics obviously are low capacity factors. In that case, as I suggested, the development of sources of storage of the energy when it is available to us from renewables is a must in our future. These are the sources of energy here in Illinois, just for your own curiosity. Our utility is the utility Ameren. It is a utility based in Missouri. In fact, 48% of the electricity we are using right now together, if you are in Illinois, is from coal. Natural gas is 23%, only 16% from nuclear energy, even though we have a nuclear power plant, right, 45 miles away from Champaign-Urbana. That is the Clinton nuclear power plant, a boiling water reactor. We'll study that in more detail later on. Some amount is coming already from wind, and renewables are being introduced. If you drive around Champaign-Urbana, you find that, of course, lots of wind power is finding its way. The Great Plains have a huge, unmeasurable resource of wind power, which is solar energy, and solar energy is nuclear energy. Anyway, nuclear energy is the mother of all energies. There is an expected growth in other parts of the world. China basically has a great plans for implementing nuclear power plant, as well as renewables, because of the great pollution that they get there from coal. Russia, India, the Europe, and the South America. And you'll notice that the spread of nuclear power all over the world, this is the distribution of nuclear power plants, is primarily in the industrialized nations. In Japan, they are restarting their nuclear power plants with safer implementations after the Fukushima accident. The Europeans, especially France and the UK, and in the United States, you find that along the East Coast and the Midwest here, nuclear power plants are associated with industrialization and the high standard of living. In terms of the top countries, in terms of producing electricity, you'll find that the United States leads the world, 800 billion kilowatt hour, followed by France, Japan, Russia, South Korea, Germany, Canada, Ukraine, China, and Spain. Germany is retiring their nuclear power plants in favor of solar photovoltaics and wind power. But they discovered that they have to import, as you read in the news, natural gas, fossil fuels from Russia, and there is probably a conflict about the supply of natural gas to Germany. So right now, they are burning what's called brown coal to produce electricity. They are polluting really on a grand scale in general. In the United States, you find that we have commercially operating nuclear power plants. Illinois here is a state that has 10 nuclear power plants in operation. The southern states also, and most of our plants really are along the East Coast. It turns out that populations like to congregate along seashores in general. That says from the United States Nuclear Regulatory Commission. So if we live in Illinois, definitely we have nuclear power generation here, especially around Chicago, because if we would be using coal around Chicago, from the graph on the deaths from pollution, you could see that we would be killing thousands and thousands of people from pollution itself. Operational nuclear power plants all over the world. We have 97 in the United States. Plant under construction are only 2. So the United States is lagging big time compared to the rest of the world. China has plans for 26 reactors, and the whole world is 63. The United States is only planning on 2 new units, and there are under construction, but much remains to be done. And the plan is to build small-size nuclear power plants, designs taken from naval propulsion. You know that nuclear power plants for producing steam are the best engine for a nuclear submarine, that it doesn't need oxygen in that case, so the submarine can remain submerged. And in fact, the first ever nuclear power plants were built for nuclear submarines. The emissions for energy produced from our Ameren, Illinois utility it releases carbon dioxide, obviously 1,372 pounds per 1 megawatt hour of energy. They release also nitrogen oxides. These are called the NOxes, and sulfur oxides, the SOxes, as you can read it, NO and NO2, SO and SO2. The nitrogen oxides turn into nitric acid, the sulfurs turn into sulfuric acid, and they get into our water supplies, they acidify them, and if they get in our lungs, they cause us disease. Very little amounts of nuclear high-level waste and low-level waste that would be like wet rags and so on used in nuclear power plants. So nuclear energy helps us produce really pollution in general. The environmentalists, as you have heard, some of them have been opposing nuclear energy, but many of them are changing their mind. So this is the in the World Future Energy Summit, You could see Jeffrey Sachs from the Earth Institute at Columbia University suggesting, quote, we are emitting about 35 billion tons of CO2 this year. By 2015, as much a larger economy, you have to be emitting less than 15 billion tons. So the world economy is going to grow by 3 times, but we have to cut back by more than half our carbon emissions. And so from that, what does it mean? It means keeping the coal under the ground. It means changing the electric vehicles. And this is a trend that's happening. You could see in town here in Champaign-Urbana, lots of those electrical vehicles, the Tesla cars driving around. It means facing the fact that our energy, when we produce power, has to be emitting 100 grams of CO2. It means telling the coal industry, unless you have carbon capture and sequestration, the coal must stay under the ground. So this is the environmental aspect of nuclear power generation. There are ways of producing power from different types of nuclear power plants. This is the PWR, that would be the design, the pressurized water reactor. And this is the dose. The dose, we'll study it later, is measured radiation dose in sievert per gigawatt thermal year. So this is the risk of producing radiation from nuclear power plants. If we use the existing systems of PWR, you could see that we have 2 orders of magnitude higher than if we recycle uranium and plutonium. And right now we are using what's called the once-through fuel cycle. We'll study that. And we need in the future to switch the uranium recycle. If we switch to the thorium type of fuel, instead of using uranium, we'll try to study that. Thorium is 4 times more abundant in the Earth crust than uranium and can be used to produce electricity. It is not being used, unfortunately, right now. We can have even a lower risk by about 3 orders of magnitude, to the point where we reach the same level of radioactivity as the uranium or the plutonium that we mined in the first place from the ground. So you mine the uranium, it is radioactive for billions of years. We use energy out of it, and then we bury back it again into the ground in a safe way. This is the expected global demand in the U3O8, that is the uranium oxide, over the period of up to 2030. So in that case, the demand of electricity is expected to grow, and the United States must be able to provide it. The fascinating thing is that there is a symbiotic relationship between the renewables, in that case, wind power generation here, wind turbines, and nuclear power plants. This is a plant that when we didn't have the COVID-19, we had a visit of the class to that plant. This is a nuclear power plant built by the General Electric Company, a boiling water reactor. And the wind turbines themselves there also were built by the General Electric Company. So these are units, the 1.5 megawatt each of the rated power of each wind turbine. This is shown here in the summer, where the wind turbines and the nuclear power plants coexist with the farmers growing their corn, and in the winter when we have snow on the ground. This is a 2-unit boiling water reactors operated by the utility that serves the area of Chicago. That's Exelon Nuclear Corporation. And the wind farm is called the Grand Ridge Wind Farm, operated by Invenergy near Ransom, Illinois. And you can go and visit there maybe and see how they can coexist together. Renewables and nuclear energy can coexist together. The future is, of course, in using more electricity. This example of a plug-in electric car. Well, of course, we developed hybrid cars where you still use an internal combustion engine as well as a battery for electric storage. But the trend is to use plug-in electric cars. And it would be stupid, literally stupid, to use electricity produced from coal and then call electric vehicles using renewable sources of energy. So the development of the renewables as well as wind power to power a future plug-in electric car system that is taking shape is the way to the future in general. Again, environmentalists are changing their mind. They are discovering that nuclear energy has great merits from the perspective of safety as well as from the perspective of pollution. So Patrick Moore is a co-founder of Greenpeace, wrote in the Washington Post newspaper in the early 1970s when I helped found Greenpeace. I believed that nuclear energy was synonymous with nuclear holocaust, as did most of my compatriots. 30 years on, my views have changed, and the rest of the environmental movement needs to update its views too, because nuclear energy may just be the energy source that can save our planet from another possible disaster, catastrophic climate change. And we talked earlier about the Fermi Paradox and the possible filters that humanity has to go to. We did mention gain of function research, creating viruses that can infect the whole world population. We are living that now. Nuclear war is another filter, but definitely climatic change is another one of those filters that can end our industrial technological civilization. He says, Mr. Moore, look at it this way: more than 600 coal-fired electric plants in the United States produce 36% of USA emissions, or nearly 10% of the global emissions of carbon dioxide, the primary greenhouse gas responsible for climate change. Methane is the other gas. Nuclear energy is the only large-scale, cost-effective energy source that can reduce these emissions while continuing to satisfy growing demand for power. So here we are in the justification for the safety and the need for nuclear energy as a non-carbon source in our future. New reactors in the two-sided states, as I suggested, 2 units are being built in Bhopal, units 3 and 4. These are in the state of Georgia, and it's a Georgia utility that's working on them. It's taking a long time. It takes a long time for building a nuclear power plant. So you have to plan for it ahead of time, about 10 years, 15 years in time. These are the foundation for those 2 Bhopal units. And look at the size of the bottom, just the bottom of the pressure vessel. These are 2 units. I think they are pressurized water reactors. It's an advanced passive 1000. We'll study what it is. That's 1000 megawatt electric. It's a safer design than the existing designs that we have in operation. It is built by Toshiba from Japan and its American subsidiary, the Westinghouse Company. So this is an advanced system that is built in the United States. As I said, the trend is to look for small reactors now that utilities can afford to build, because those large nuclear power plants can cost, in the case of about $10 billion a unit. So the financial crisis is still there. There is a dearth of capital. The small units can cost maybe $200 million a unit. So this is the way that utilities think they'll be building nuclear power plants in the future. So this is the proposed United States electric generating plants in 2018. The emphasis, as you could see here, is on natural gas. But as I suggested, natural gas is a depletable resource. Natural gas that the United States has right now is more like from fracking or from tight formations. What you do, I'll describe it maybe in one of the lectures. You drill a hole, then you drill horizontal piping in the formation itself. Then you pressurize water mixed with sand. You use a gun to perforate the tubing, create cracks in the medium by putting water with sand under high pressure, 8,000 psi, and enhance the production of natural gas. But at some point, you have to repeat the process of cracking or hydraulic fracturing several times, and then you have to use chemicals to for that water that you use, and then you have to dispose of it. So it is not a continuous or a sustainable process. Some people have even complained about the water that gets injected into the ground, used as a lubricant and causes earthquakes. People in Oklahoma had a higher frequency of earthquakes in general. So this is the proposed electrical generating plant as of 12/18. Natural gas 65 gigawatt electric, wind 21, and solar photovoltaics 11%. So you'll have to add here 67 electrical producing gas, natural gas. Again, still the dependence is on fossil fuels. No mention here of nuclear power plants. So the United States, unfortunately, is lagging in the process in general. I'm going to bypass these ideas of economics here, but the challenge for our engineering profession is, of course, to face the situation of the introduction of robotics and industrialization of the production processes. And you'll find that to make a future for our young engineers, we need to prepare them for a future of high technology in general. If you want to read more, you can read about the systemic reach of climate change cure as an appendix by Geoffrey Pohanka, and this covers our preface or our introduction to nuclear power systems. I'll stop the sharing here and allow for maybe some questions in the chat room. Let me see if I can do that. So if you have questions about that chapter before we switch to the next chapter, I'll be happy to answer them. After the lecture, we still have a half an hour to go, as you could see here. I'll be available all the afternoon for any questions that you have. All right, so I don't see no questions here. So I'll start use the energy that we have and start sharing. And in that case, we go to the first chapter in our lecture notes. So we backtrack here and we start talking about the first human-based reactor that was built. And the fascinating thing is that, as you will see, that it was built here in the state of Illinois. And it was in Chicago, rather than Champaign-Urbana, obviously. And in that case, we'd like to study the past because it explains our present and guides us into the future. Something important to notice here is that there is a distinction between a nuclear reactor and a nuclear device, in the sense that a nuclear reactor cannot explode like an atomic bomb whatsoever. I can describe that to you in more detail later on. And we go back to the future of the ascent or the birth of nuclear energy. As I suggested, it was the first reactor in the world ever operated at the Stagg Field at the University of Chicago. And it was, we come back to Mr. Enrico Fermi. Enrico Fermi was a scientist that was in charge of the project. And they called it the Chicago Pile #1. And you'll see why. Obviously Chicago, because it was built in Chicago, but we'll see why they called it a pile, because it was a pile of a moderator that is graphite. Graphite is really a very common material. When you use a pencil, you think that it's a lead pencil, but it is not really lead that you use in a pencil. What you use is graphite, and graphite is nothing than a form of carbon, primarily the isotope of carbon, carbon-12. So it was a mixture of graphite or carbon, and it was used as a moderator and the fuel the fuel was natural uranium-235, and uranium as an element that we get, of course, from the Earth's crust. There is no pictures of the event where the first reaction happened, but an artist, Gary Sheehan, provided us with a painting that described the process, and we can describe it here. The first important aspect of it is that it was a pile. And you could see the pile is colored in black, enclosed in some wood kind of planks. Inside those piles, you see a structure here of holes that we come back to later. So it was a pile of graphite blocks with uranium fuel enclosed in them. The event happened on December 2nd, 1942. This is a squash field here. On the top here, you see a group of scientists standing, among them our Enrico Fermi here, who was the leader of the project. The same Enrico Fermi that came up with that Fermi Paradox. Where are the aliens? The fascinating thing is that the components of the Chicago pile number 1 are basically the same components as the large reactors that produce power today, except that the power or the energy that it produced was only 1/2 of a watt of energy. And maybe I should ask you to go and check for yourself the power that is produced in an existing electrical producing nuclear power plant. You'll find it's 3,000, not watt, but 3,000 megawatt, 3,000 million watts of power. So it's a great leap for humanity from the 1/2 watt produced as power in that whole big pile here and the pile that we get from an existing power plant. All right, so we have the components were the following. A graphite as a moderator, will describe why it is a moderator, the fuel, and then you find here those lines that have what we would call control rods. These are rods of steel, maybe, or any material that absorbs neutrons. For instance, indium absorbs neutrons, boron absorbs neutrons that can be inserted or withdrawn from the pile. And because they can absorb the neutrons and neutrons are causing fission, if you insert the control rods, you decrease the fission reaction. If you pull out the control rods, you increase the fission reaction. The whole enclosure was enclosed inside a large rubber kind of balloon from the Goodyear company. In case of an accident or release of radioactivity, they didn't have to use it. And then they had a group of people standing there on top with buckets that contained boric acid. Boric acid contains the element boron, and boron is a very strong absorber of neutrons, so they can shut the chain reaction. What they were doing here, as you could see, is that they were creating a pile, and in that pile, they were adding one layer upon another layer upon another layer of that mixture of the graphite, the moderator, and the neutrons. And what they were doing there is attaining a critical mass. We'll study by the end of the semester how to calculate what would be the critical mass for a nuclear reactor. And that is the secret of the nuclear age, where your group of students becomes privy to compared to other students in the rest of the world. That group of people sent to Washington, D.C., where people were overseeing their activity, the following telegram. A quote, "You will be interested to know that the Italian navigator has just landed in the New World and the natives are friendly." The Italian navigator alluded to was not Christopher Columbus, but Enrico Fermi. He was born in 1901, died relatively young here, 53 years of age in 1954. The code part, natives were friendly, alluded that, oh, they succeeded in that major experiment that is called CP1 or Chicago Pile number 1. And so nuclear energy was born basically on that monumental or historical December 2nd, 1942. 42. None in the audience and none of their parents, not even the instructor myself were born at that time. So this is history that we are living here in that case. Here is a picture of Enrico Fermi. We mentioned the Fermi Paradox that we described earlier. If you live in the vicinity of Chicago, you may have heard or visited Fermi Lab. Fermi Lab is named after Enrico Fermi. He was a scientist from Bologna University. He came to Columbia University in the United States before the World War II. The winds of war were basically getting people concerned in Europe about fascism from Italy, Mussolini, and Nazism from Germany, Hitler, and so on, burning of Europe. Mr. Fermi, Enrico Fermi, was adherent to the Catholic faith. He was Christian. He was married to a wife adherent to the Jewish faith. And of course, Nazism was not very friendly with the Jews. So they emigrated to the United States. And he was an expert in the behavior of neutrons. And he became in charge of that project for building the Chicago pile number 1. One interesting aspect of the pile is that it was a mixture of the graphite or carbon and uranium. Uranium was the fuel, carbon was a moderator. Why is carbon there? Because Enrico Fermi was smart enough to understand that the neutrons behavior with the uranium is a quantum mechanical effect. So the neutrons in that case behave more like waves. So contrary to the intuition, where you would think that a very highly energetic neutron can fission a uranium nucleus when its energy is very high, that is not true. The nucleus acts more like a potential well. The neutron acts as a wave. So the lower the energy of the neutron, the higher the probability of its fissioning the neutron. In that case, the neutrons are born from the fission process having a kinetic energy of 2 million, that's a million here, electron volt. The electron volt is another unit of energy. Today we looked with 3 units of energy. We looked at actually, the joule, we looked at the BTU, and now here another unit of energy is the electron volt. What's the electron volt? The electron volt is a kinetic energy acquired by a neutron when it is accelerated through a potential of 1 volt. So we call it the electron volt. 1 million of those electron volts is the energy, 2 million of these electron volts is the energy where a fission, neutron coming from fission is born. We need to bring it down all the way to the thermal energy where it becomes in thermal equilibrium with the medium. So we use a moderator to have that neutron collide with the nuclei, not the atoms, the nuclei of the graphite in that case, and multiple collisions brings its energy from 2 million electron volt to the 0.025 electron volt. If you remember your thermodynamics, that's a kT energy. T is the Kelvin's degrees, and K is the Boltzmann constant. So you're reducing the energy of that neutron from 2 million electron volt to 0.025. You are reducing the kinetic energy 80 million times, 80 million times. And it was known to Enrico Fermi that those neutrons have a higher probability of causing fission than the high energy neutrons at 2 million electron volt. And that explains why we have a mixture of graphite, carbon, and the uranium in the Chicago pile number 1. All right, so that's 80 million reduction in the energy of the neutron. And this is a picture now that is provided to us, that probably the only picture of the pile itself. That's a layer number 10 here. You could see here in that on that plate. And as I suggested, it was a layer upon layer. That's why they call it a pile. It was piling of blocks of graphite. You could see blocks here. And those round spots in it are really balls of uranium. And this is the, I think, the 10th layer. And they were adding layer upon layer until they reached a what we call a critical mass. Now, the genius of Enrico Fermi is that he separated the uranium from the graphite. And this is called the lumping the system. Now, what happens in that case is that a fission can occur in that uranium ball. A neutron is born. It finds time to reduce its energy by scattering in with the nuclei of the graphite. And after it loses its energy, then it can find another ball of uranium and cause fission on it in it because it has reached now a very low energy. The Germans, on the other hand, where, as we'll see later, fission was discovered, did not understand that. And what they use is a mixture initially of uranium in a slurry of another moderator, heavy water. So the uranium, the neutron born in the fission process does not have time to lose its energy to interact with some other uranium. It gets absorbed immediately in the uranium in the slurry mixed of a mixture of fuel and moderator, and they were not able to produce the same results as the Chicago pile #1. So this is the 10th layer. One student in our class had his dad work on the project, and as a souvenir, he has one of those blocks of graphite. So this is a real picture of it. Paul Mickels was one of the students taking that class. So it says here graphite from Chicago pile #1, first nuclear reactor, and the date that we mentioned, December 2nd, 1942, at the Stagg Field, the Swash Field at the University of Chicago. So that basically was the composition of the reactor, graphite as a moderator and uranium as a fuel. In modern day reactors, you find we have different moderators. We use water, ordinary water as a moderator. We call that type of reactor the pressurized water reactor. Or we can use heavy water, that's what we call the heavy water reactor. You could use graphite, in fact, as a reactor for high temperature gas cooled reactors. So the moderator is replaced by water in modern day nuclear power plants, and the fuel is still uranium. You'll find that some components like the control rods are still have to be used in modern day reactors. The safety systems that boron buckets can be also used in boron injection as a safety measure in present day reactors. So the same components exist, except for the power level. 1/2 of a watt of power in the Chicago pile #1, 3,000 million or megawatts of power in modern day reactors in general. That effort, of course, was happened during the Second World War. So the information was classified, but then a patent was filed after the war in 1955. The war ended in 1944. And you could see here the components. Actually, you can go to the patent office and look at the patent yourself. The patent number is 2,708,656. You could see here that they describe the control rods coming in and out from the nuclear reactor to control the chain reaction. So this is a feature that exists in existing nuclear power plants. So here we differentiate between, now we become a little quantitative, between thermal and fast neutrons. Fast neutrons are those neutrons born in the fission process. We said that they are born with an energy of about 2 million electron volts. Thermal neutrons is those neutrons now that have thermalized, meaning that they lost their kinetic energy and they are in thermal equilibrium with the moderator itself. So if you say that the thermal neutrons are thermalized, then you describe them in thermodynamics as their kinetic energy, E sub k, is equal to the Boltzmann constant multiplied in their Kelvin temperature. And we all know that in thermodynamics, We don't use degrees Celsius. We add to it 273, and that's what we call the Kelvin temperature. So in that case, this is the kinetic energy of the neutrons at thermal energy. And if you suggest that the KT neutrons have a kinetic energy of half mv squared, like in mechanics, this is the kinetic energy, you can estimate the speed of those neutrons. And we get here something very interesting. Just use the scissors rule. Twice the kinetic energy is equal to mv squared, and then bring the m to this other side and take the square root of v squared, and you can calculate the speed of the neutron. It's not a vector here because it doesn't have directional properties, but the square root of twice the kinetic energy divided into m, the mass of the neutron. So if you know the mass of the neutron, and they know the temperature at which the neutron is occurring, we know the Boltzmann constant, we can calculate really the speed of that neutron. And you'll find something very interesting in that case is that K is a Boltzmann constant in ergs per Kelvin, 1.38 10 to the minus 16. T at room temperature, let's take room temperature 20 degrees Celsius plus 273, and then convert that erg, which is another unit of energy that we learned about today. Remember, we learned about the joule, we learned about the BTU, we learned about the electron volt, and here this is the conventional system of units of energy, the ergs. As engineers, we must be capable of dealing with all those different systems of units, especially if you are dealing with energy production. So you convert your ergs into electron volt, and the conversion factor is 1.61 10 to the minus 12, and you get that 0.025 electron volt of thermal, the energy of the thermal neutrons that we mentioned earlier. And this is the kinetic energy, 0.025 approximately. From that energy equation here, number 2, we can calculate the speed of those neutrons. So by taking the KT as 0.025 electron volt, you convert your electron volt into joule. This is the conversion factor is 1.6 10 to the minus 19. You get this from Wikipedia, or you get it from the handbook of physics and chemistry. And joule and joule cancel, the erg with electron volt cancel, and you find that the mass of the neutron is 1.6 10 to the minus 24 grams. We cannot have a scale that measures this, but we can calculate it. And you'll find that the speed of the neutron at thermal energy is 2200 meters per second. So that neutron moves really, really, really fast. And because it moves so fast, it just suggests that it behaves more like a wave rather than a neutron. There is an analysis here that I use theory of relativity for the same process to calculate the speed of the neutron, its kinetic energy. It doesn't lead to very different results. So I'll just show you some of the detail, but instead of getting 2200 meters per second, we get 1.95 10 to the 9th centimeter or 10 to the 7th meter per second. Something related to the Chicago Pi #1 operation is the word scram. When you heard maybe the word scram, when you have to shut down any kind of mechanical device, you push a button and you shut it down. That was the word used to describe those group of people at the top of the pile. And the story goes that a gentleman named Norman Hilberry, title was the Safety Control Rod Axe Man. So if you take SCRAM, that is scram. So when you say scramming something, this means shutting it down in a suddenly way. And that's what operators in nuclear power plants use when, if they have to insert the control rod suddenly into the reactor, they scram it, they push a button, all the control rods come in and shut down the reaction. Another name for it is the RX trip, tripping the reactor in general. We leave for next time the cover of the scientific milestone that led to the fact that we had that first reactor built, and I'll change the assignment to introduce some of the material that we covered. We covered more material than expected. Thank you for your attention. That's all for today. I invite you to read the material, obviously, and as you read the material, work on the assignment. I'll change the assignment because we covered more material than we were expecting. Okay, I have questions in the chat room. The lecture has